Okay. Well, thank you. It's a real pleasure to be here. When Arjun, man? Oh, I see. Okay, you play with it. So when Arjun asked me to come here and speak for a few minutes to hear about the history of quasicrystals in the LRSM, I looked at my calendar. I saw that I had two conflicting commitments the same day already, but I made a point of managing to shove things to earlier in the day because I really wanted to be here to take part in the celebration. The LRSM had a really profound impact on the history of quasicrystals. It's, I think, an interesting example of risk-taking, high risk-taking, even higher than most risks that the LRSM has taken historically. And it certainly made a very important contribution to my life, to my scientific life, and to that of my students, postdocs, and collaborators. So while we're still waiting, let me begin by saying, whereas most of you probably, when you came to Penn, came here with the notion already that you would be working in the LRSM and working with colleagues in this area, in this cross-disciplinary fields, I should explain that when I was recruited to Penn, I was recruited in the high-energy group. A lot of my research is in high-energy physics, although I had been doing some work on the side in condensed matter physics and material science, dating back to undergraduate days. And actually, Mark Brodsky, who played a role in influencing me in that direction. Okay, well, I'll try to continue the story anyway. So at the time, shortly after getting to Penn, I was invited to give a colloquium, a physics colloquium. And there I spoke about work I had been doing recently with David Nelson and Marco Ronchetti. I decided to talk about something in the condensed matter area. And I talked about work done with David Nelson and Marco Ronchetti on icosahedral bond orientational order in supercooled liquids. So what we had been studying was on the computer supercooling a monodispersed liquid of Leonard-Jones atoms, atoms that are interacting through Leonard-Jones forces, and studying the orientational order. So you study the links between atoms and their neighbors here and there, and then compare their orientations in space. And what we had noticed was that there was a correlation, an extended correlation in those orientations that you wouldn't have expected in a liquid and glass, which you think of as being translationally disordered. In this liquid or glass, there seemed to be a sort of hidden orientational order. Now, it wasn't long-range orientational order. It was extensive, out to 8 or 10 atomic distances. But this was a monodispersed system and only a first attempt. So at the end of the colloquium, I speculated that, as far as I could tell, it was possible in principle that that orientational order might be extended out to infinite distances in some appropriately chosen system. It was just a wild speculation. But after the talk, a young student came up to me by the name of Dov Levine, sitting in the back there, and he said he wanted to pursue this idea, trying to see if we could really make this structure, and if this could be possible from real materials. Well, I told him that this was a really high-risk problem, that it wasn't even clear that it was mathematically possible, let alone physically possible. But he persisted, I would say foolishly persisted, and so the project began. And shortly after then is when I really got my first real acquaintance with the LRSM. It was Paul Sovin who actually brought the possibility to my attention. This is a draft of a note that I wrote to Ward Plummer at the time, explaining that Paul had suggested that, at least as far as for supporting Dove, that we go to the LRSM for support and for support of our project. And I mentioned that Dove and I will be studying the consequences of bond orientational order in supercooled liquids and glasses. And sort of hinting at our idea, I said I believe that there are potentially many interesting problems in this field. And I didn't really expect much from this, but I was surprised that, in fact, the LRSM came up with seed money to support this this high-risk effort with this high-risk, unconventional person at the helm. We tried, Dov and I began then working on the project based on this seed money, and after a period we came to various ideas for trying to get extensive long-range orientational order with icosahedral symmetry. And somewhere along the way, Dove brought to my attention this tiling, which is known as a Penrose tiling, which was constructed in 1974 by Sir Roger Penrose. Now, when Penrose constructed it, he was trying to construct a tiling which was, he described as simply non-periodic, suggesting, well, at that time, you would have either said something was periodic or disordered. So if you said it's non-periodic, it would suggest a kind of disorder to it. But what was interesting to us is it had these local centers of five-fold symmetry, and that each of the edges of these tiles is oriented along one of the edges of a pentagon. So this hinted of a kind of five-fold symmetry, even though five-fold symmetry is forbidden for crystals. And so that was the hint. That suggested that maybe we could accomplish something like that. Similarly, for icosahedral symmetry in 3 dimensions, provided we could understand what was going on in this tiling. And the key to understand what was going on in this tiling was to decorate each of the fat tiles with these little line segments here, and each of the skinny tiles with these line segments here. This decoration was first suggested by an amateur mathematician by the name of Robert Amann, and so they're called Amann lines. And if you put together the tiles with those decorations, they end up forming continuous lines that go across the entire structure. So now, if you had some doubts about whether this structure was random or not, it's clear that it's not random. It's clear that when I put down a tiling over here with a line segment in this direction, it forces infinite lines of tiles in 5 different directions at the same time. So it clearly has some kind of order to it. On the other hand, if you study the lines in each of the 5, you find there are 5 sets of lines along 5 different directions, along the directions of a pentagon, the edges of a pentagon. You find that all 5 of them are the same. It has a 5-fold symmetry, and that's forbidden for crystals. So how is this possible? That was the question. It turns out the secret is to look at the patterns of lines more closely and notice that if you follow the patterns of lines in any one direction, there are only 2 spacings between lines, long and short, where the ratio of the long length and the short length is the golden ratio, an irrational ratio. And the sequence of spacings, long, short, long, short, long, long, short, long. If you follow it out, it follows a sequence of what we call a Fibonacci sequence, where the ratio of the longs to the ratio of the shorts follow a ratio of subsequent Fibonacci numbers, which in the infinite limit approaches the golden ratio. That's an irrational number. So again, that confirms the fact that this can't be a crystalline structure that we're looking at. It must be a structure which, if any crystalline structure would have to have a rational ratio, there must be something else going on. And there is something else going on, because a Fibonacci sequence is not a random sequence. It's a very special sequence. It's one that can be decomposed into a sum of 2 periodic functions where the ratio of the periods is irrational. Such a sequence is very special and is referred to as a quasi-periodic sequence, and hence that led to the idea of quasi-periodic crystals, or quasicrystals, the idea that we could generalize this idea to other symmetries and other dimensions. Once you had this key idea, this quasi-periodicity, it was kind of an aha moment. You could then realize that you could repeat the same trick using different sequences with the same concept with different symmetries. In fact, all the symmetries that were forbidden for crystals are now allowed for quasicrystals. In particular, the most famous forbidden symmetry was the symmetry that I had been studying with Nelson and Ricchetti, which was icosahedral symmetry. And what Dove and I were able to do was construct a set of units, these little rhombohedra here with little magnets in the corner, which have the property that if I give you a room full of those units, you can fill this room with them and close pack with them, but only in such a way that they form precisely this icosahedral quasicrystal, an icosahedral structure with quasi-periodic order. And that was important to our thinking because it suggested that you could imagine atoms or clusters of atoms acting in a sort of isomorphic way, acting in a way through short-range interactions that they would be forced. Their lowest energy state would correspond to a state which was quasi-crystalline. Now, this was nearly 2 years into the seed funding, and we were working on this very abstract hypothetical idea. I was feeling a little bit embarrassed that we had not yet made any connection to real materials. And in fact, we had, in a review that we had received. We were told this is all very interesting, but it seems to have no contact with real materials. We endeavored at that point, at least we endeavored at that point to at least try to patent the concept as a sort of toy and architectural design concept, and that's where we introduced this term crystalloids that Paul Chaikin mentioned before to represent these features, and we talked about the possible use of materials. But of course, it was all hypothetical then, and but at least we had something to show for our efforts. Now that we knew the secret to the structure, and we knew that we could have the structure be forced, in principle, through ordinary energetic interactions between atoms, the next task was to see if we could find a real material that would have this quasicrystalline property. How would you recognize it? Well, the next thing was to compute its diffraction pattern. Now, because it's not random, because it's not disordered, because it is quasi-periodic, its diffraction pattern can be decomposed into the diffraction pattern of the two periodic functions which compose the quasi-periodic sequence, plus all linear combinations of those wave numbers. So when we computed the diffraction pattern, what we discovered is that the diffraction pattern consists of true Bragg peaks, just like you would have for a crystal, but arranged in a pattern which had a non-crystalline symmetry, tenfold symmetry, something that would be completely forbidden and completely shocking if you were to have seen it in the laboratory. Now, by now, many years later, we're used to the idea that quasicrystals have these Bragg peaks. But at the time, it was strongly believed, the conventional belief was that the only kinds of structures that can have true Bragg peaks were crystals, periodic systems. And here we were saying that no, here were systems that were non-crystalline, which violated the laws of crystallography, which have true Bragg peaks. Not only is it obvious, and not only can you recognize this quasicrystallinity from their forbidden symmetry, but another feature is that because of this competing incommensurate periodicities, one finds that between peaks there are yet more peaks and yet more peaks. We've only cut it off to a certain level here, but there's kind of a snowflake or fractal appearance to the diffraction pattern that makes it immediately recognizable when you see it. So again, all this was abstract. By fall of 1984, I decided to plan to take a leave at IBM Research, leave from Penn, to see if we could convince people to try to look or fabricate structures with this property. On October 10th, after having been there only a few weeks, we were visited by David Nelson, who had been this collaborator several years ago. We hadn't really talked much since, but Dov and I were there that day at IBM, and we were anxious to explain to David the progress we had made in calculating the diffraction pattern and showing that you could have these new kinds of structures, at least in principle. David entered the room saying that he had something he wanted to show us. He knew nothing about the work we had been doing, but he had an interesting preprint he wanted to show us, which had something to do with icosahedral symmetry. We figured a little bit about who would speak first. He got to speak first. And what he did is he showed us a preprint by Dan Shechtman, Ilan Brecht, Denis Gradius, and John Kahn, which talked about this peculiar phase of aluminum and manganese, which diffracts electrons like a crystal, but one with a symmetry strictly forbidden for crystals. And we flipped through the pages, and after a point, we got to a page which showed this diffraction pattern. And at this point, I don't know if we literally left off our chairs, but figuratively we leapt off our chairs. I know that I walked over to the table and then lifted off the table this calculated diffraction pattern that was sitting there. That's the one we were going to show David. And, of course, we were very excited to see the close correlation between these. And that's how the story began, so, at least from our perspective. I think within hours, I had called back to Tom and others here at Penn and at the LRSM to explain the exciting development that had just taken place. And we wrote a paper very quickly within a few weeks. And December came back to here at the LRSM in this room. And this was actually where the first public presentation of the theory of quasicrystals was made. And it was a great time. It was very exciting. I felt very grateful to have the opportunity to return something to the LRSM for having taken all this risk on our behalf. And this was the paper with the actual published title there, with quasicrystals as being the name, short for quasiperiodic crystals. Well, that was just the beginning of a really exciting period for me, for our group, and here at the LRSM, essentially laying the foundations of the theory of quasicrystals. So, over the next year, 1985, a whole series of wonderful collaborations began with Tom, with Paul, with Stellan Osland, and Paul Heine, both experimental and theoretical. There were also postdocs, Sriram Ramaswamy, Peter Bansal, Josh Sokolar, Kevin Ingersent. I think some of the other names didn't appear there. David Wright and Takeshi Agami were others. And here I've just begun to give the first few papers that came out of these collaborations, which really laid the foundations, both theoretical and experimental, for the field. So on the theoretical side, I think the most important work was in working out the elasticity theory, the novel elastic properties of quasicrystals, the fact that they have, in addition to phonon hydrodynamic modes, another set of hydrodynamic modes known as phasons, which are unique to quasicrystals and give them a lot of interesting, unique physical and physical properties. And on the experimental side, working with Paul Heine and Peter Bansal, a lot of the foundational work on the first quasicrystals and then later quasicrystals would be discovered was done. And I think the most important work in establishing the quasicrystal theory as being correct came out of this experimental work. So although there was this nice match between what Shechtman had found in his electron diffraction pattern and what we had calculated, in fact, closer examination by Paul Heine and Peter Bansal and others revealed that in X-ray diffraction, those peaks actually have a finite width, whereas the quasicrystal picture really predicts that the peaks should be truly Bragg. But later materials that were discovered elsewhere later, like a mixture of aluminum, copper, iron, when we studied here at the LRSM with Paul Heine and Peter Bansal, were revealed to have true resolution-limited Bragg peaks and really quashed all the competing ideas for explaining these materials, such as Linus Pauling's multiple twinning model, or the so-called icosahedral glass model, a disordered icosahedral glass model, and really made clear that quasicrystals are something that can really be made in the laboratory. And well, that first year and the next 5 years to follow produced a lot of important results. That really isn't the end of the story. Paul Chaikin already pointed to one set of developments that it continues to this day, which is this work on photonic quasicrystals, beginning to take advantage of the quasi-periodicity to obtain unique transport properties. Meanwhile, another direction, which is also seeded in a sense here at the LRSM, involves the search for natural quasicrystals. So the connection is that in one of the projects that I worked on in association with the LRSM was with Takeshi Agami and Vasek Vitek. In the course of working with them, they pointed out to me something which you know existed, but I didn't know existed. It's called the International Catalog of Powder Diffraction Patterns. And it's a catalog of 80,000 or more patterns, about 9,000 synthetic ones, and about 9,000 natural patterns from natural materials, and the rest synthetics. It triggered an idea in my head, which was this would be an interesting way to search for natural quasicrystals. This is something I'd been interested in actually early on. I'd been going to museums trying to see if I could find natural quasicrystals there by accident that might have been stored in the museums by accident and misidentified, and that hadn't worked out very well. But with this powder diffraction catalog, it seemed that one could do, in principle, a computer database search for powder diffraction patterns which were nearest approximants to known quasicrystals, and then go after those, see if any of those turned out to be a real quasicrystal. So I had that idea in my head. I even tried it with one student here. That didn't quite work out very well, but I tried it again a few years later, 1999, once I moved to Princeton with a bright young undergraduate doing a senior thesis, Peter Liu, And that began, and we ran this computer database search and identified about a dozen natural materials that might be good candidates. And then we began to scour the world for them and see if we could find them and test them. In the process of scouring them, we found this rock, which is a very complex rock. It contains all kinds of common minerals in it, like olivine and diopside and other things. But it also contains copper, aluminum alloys. And inside, we found a beautiful, beautiful grains of perfect quasicrystal. And through a forensic search that took about 2 years to pursue, we managed to trace the history of this rock, because we had to know for sure that it was natural and where it came from, all the way back to this remote place in the far eastern Kamchatka Peninsula in the northern province of Chukotka, right there where that pin cushion is. And just to show you that, how the LRSM can lead to really wild adventures, we actually went there this past summer. I actually organized a geological expedition there that went back there. We gathered lots of about 1.5 tons of material from this region to see if we could find any more examples of this rock. And sure enough, we did. We did find more grains of this material. Here's a grain of this material. It's mostly not quasicrystal. Only a small piece of it there is. But that little shiny grain there, when you take its X-ray diffraction pattern, produces a beautiful tenfold diffraction pattern. And it has a composition which we immediately recognize because it's the same composition as a material that was studied by Peter Bansel and Paul Heine here at the LRSM back in the 1980s. So the only difference is that when Paul and Peter made it, they made it here synthetically here in the laboratory. It turns out that this rock that you're looking at, that's the trap that we found it in, is a meteorite. And so it's an ancient quasicrystal, and not just a little bit ancient, but this particular kind of meteorite is the kind that formed at the very beginning of the solar system, before the Earth formed. So it's not just a little old, it's 4.5 billion years old. And since it formed in the solar nebula, before the Earth formed, it's one of the first kinds of solids to have formed in the solar system. And since it formed in our solar system, there's no reason we think our solar system is unique. It's probably one of the first solids to have formed in the galaxy. So quasicrystals have gone from this over this 30 years period, from one of the newest kinds of solids to have been discovered by humans in the laboratory to one of the oldest solids to have been made in the history of the universe. And who knows where the adventure is going to take us next. So I just want to say thanks to all at the LRSM for supporting this high-risk venture. Its venture continues, and I know I appreciate it, and happy 50th anniversary.